Okay, so we can start. Yep.
Yes, we can start.
No, actually, my time is far ahead than Kiev and Kharkiv right now. Yeah, but today we're talking about transactions and blocks in Ethereum, so how they are structured, what are their purpose, what's inside of those transactions and blocks, and actually why they're needed. So first of all, let's define a transaction. So transaction is an atomic action initiated by an externally owned account that either changes the Ethereum state or reverse. So from the previous lecture, we remember that Ethereum is a state machine, which has states that are globally accessible. So you can read those states anytime you want. It is free, but in order to change the state, you have to initiate a transaction that applies some changes to Ethereum, either transfers Ether or interacts with a smart contract that writes something to its state or emits events, and transaction changes the state to T+1 from state T. Transactions are atomic, which means that if anything happens inside the transaction, it either completely applies or reverse. So it can't partially do something. It either does it completely or reverts the changes before the transaction was initiated. In Ethereum, only external owned accounts can initiate transactions. So contracts can only listen to the transactions and react. And also contracts can call other contracts, but they cannot originally make transactions. So in Ethereum, there are three main types of transactions: regular ones, the contract deployment ones, and the ones that interact with smart contracts. So the first one's regular. It is just basic, the most cheap transaction that you can initiate. It is the one that sends Ether from one account to another. It costs 21,000 gas. We'll talk about this in future lectures, how gas is estimated and how Ethereum virtual machine understands how much it has to consume and how much the user has to pay. But for now, understanding that regular Ethereum transaction, it is the simplest action anyone can do with Ethereum, and it is the cheapest. Then there is a special deployment transaction where the to field of the transaction body is set to address 0, and a special data field is supplied with the smart contract creation bytecode. Those deployment transactions are really expensive because per deployment byte, you pay 200 gas. So if you want to deploy a regular ERC20 token, which might be several kilobytes in size, it will cost you several million gas. And the third type is when the contract is already present on the blockchain, and you can specify the smart contract address to a 2 parameter and supply the data field with the execution payload. So this execution payload is the specially encoded data encoded with the ABI standard application binary interface standard, which the EVM decodes and provides to the execution, like execution bytecode of the smart contract, which further understands what to do with it, and the corresponding function is invoked. Those smart contract interaction transactions are the common right now. So the majority of transactions are this one, because there are a lot of smart contracts and everybody interacts with them. Okay, so what is inside an Ethereum transaction? So first of all, there are a lot of fields, and in order to construct the transaction, every field has to be specified and then encoded and signed. So when the transaction is signed, it is sent to the node, and the node verifies that the signature is valid, and that is how it understands who initiated the transaction. If we look closely at the fields, we have a nonce field. It is actually one of the most important ones because it stands for the special nonsense that prevents the transactions replay. So basically, it is the special counter that Ethereum maintains, and it means how many transactions has externally on the account initiated. And every other transaction will have this field incremented. If you're talking about smart contracts, there is a nonce present for each smart contract, but it is not the originally initiated transactions. It is how many smart contracts has this smart contract deployed. But still, for every smart contract, there also is this special nonce. Then we have two fields that stand for the gas. Those fields are introduced, were introduced after the London hard fork. So prior to London hard fork, those two fields were just regular gas price. It is the amount of Ether that you're willing to pay for every single unit of gas. But after London hard fork, this is changed, and this basic auction-based model has changed into the two variables. So first variable, it is the max priority fee per gas. It is just a simple gas price as it was before. It is the amount of Ether you're willing to pay directly to the validator that will include this transaction into the block. It is called the validator tip. And then there is a second one. This variable stands for the sum of the priority fee plus the base fee of the block. So after the London hard fork, the base fee of the block was introduced. We have covered this slightly in the previous lecture, and this is how Ethereum maintains its load. So when the load is high, everybody is sending transactions, so Ethereum has to adjust, to compensate, and the base fee per block rises, which further increases the cost of the transaction, and the load decreases. And this variable in the transaction is needed to cap the fee plus the base fee of the block, so the user won't overpay. So the description is here, says exactly that. So it is the base fee, block base fee, plus the priority fee. And then we have the gas limit. The gas limit is supplied by the user. Usually it is calculated by the wallet. So when you are sending a transaction, the wallet will automatically estimate how much gas the transaction will consume and provides the gas limit automatically. And if the transaction runs out of gas, it just reverses. This is needed, for example, when smart contract uses an unbounded loop or infinite loop, and sending like arbitrary transactions into the smart contract would like decrease the balance of the sender by a lot. So to prevent those kinds of errors, the gas limit is set, and it just caps the total execution of the transaction. So you're like confident that not more than this gas and Ethereum and Ether like won't be deducted from your account. Then there is a recipient. It is a regular Ethereum address. It can be pretty much any value, and even there might not be a private key for the address that can be set to a recipient, but you can send funds to this account. For example, address 0, there is no private key for such an account, but still you can send transactions to this account. Value, it is the amount of Ether, but actually way that you're willing to spend. Way, it is the smallest amount of Ether. It is 1 to the point like 0, 17 zeros and 1. So 10 to the negative 18. In Bitcoin, we have 10 to the negative 8. Here we have 10 to the negative 18. And this value is set to this huge number, which means how much Ethereum you're willing to spend. And the data field, which is this execution payload, usually it is being encoded when you're interacting with the smart contract, or it can be the actual bytecode on the smart contract if you're deploying it. But you can specify pretty much anything there. And for example, you can encode photos and store the raw bytes of this encoding in the data field, and then, for example, read this transaction and decode the photo if you want. And the last fields are the VRS parameters. These are the parameters of the ECDSA signature. So when the transaction is constructed, it is signed with the externally owned account's private key, and the signature is obtained, and then it is encoded and sent to the nodes for the validation, and then addition to the blocks. Okay, just let me quickly scroll through the chat. Can transaction be initiated only by external on account and by smart contracts? Yes, only externally on accounts can initiate transactions. How Node differentiates between real and fake transactions. So actually, Node has a lot of protection mechanisms. So first of all, it checks the validity of the data. So for example, I don't know, value can't be negative or something like that. Then it might check that the signature is valid, might check that the user who is like sending the transaction is recovered from the signature, so and something like that. Then it checks that the amount of Ether that the user possesses is higher than the specified value plus the gas limit multiplied by the max fee per gas, and etc., that the nonce is valid. And if each of the cases passes, then the transaction is included into the mempool, where it's going to be picked by the validator and then included into the block. So, and if the transaction is still invalid somehow, and then there is a consensus, proof of stake Ethereum consensus, that checks every block and votes for the validity of each block. If there is something wrong with the blocks, blockchain reorganization happens, and this particular transaction and everything that is included into the block may be just discarded and like returned to the mempool, and this fake transaction excluded at all. Could you make a brief overview of type of transactions again? Yes, so 3 types, and regular one that just sends Ether from one account to another. The smart contracts deployment transaction, when you specify the destination address to 0, and the data as the bytecode of the contracts you're deploying. And the third one, when you're just interacting with the smart contract, where to field is the smart contract and the data is the ABI encoded execution payload. Will max priority fee per gas lease be used up to maximum by the validator? I think it's reasonable for the validator to always get the maximum amount of money possible while looking at real transport. Okay. So no, validator will not consume whatever like you said, because first of all, there is a cap on the priority fee per gas. So this one will be consumed like 100%, but you can specify this max fee per gas to a higher limit, and this will account for the base block fee. Because like your transaction may take several like seconds or minutes to get included into the block, and the load of Ethereum may either like rise or fall. So this will account for that. While looking at the real transaction load, I also saw a field called August Bloom. Could you please describe what is used? So it is not in the transaction. Logos Bloom is the field in the block itself, but what it stands for is the logs that contracts emit. They're placed in a special like data structure, and this logs bloom is just like this data structure like some kind of representation of this data structure that enables quick access to the events, so you can quickly understand. So you can quickly understand what has happened, and yeah, it's just like data structure that is optimized for this specific role to get quick access. Okay. Several transaction facts. First one is EAP 718 introduced a transaction envelope to support future transaction types. So this EAP was like a part of London hard fork, and it introduced a special like envelope that enables users to specify which type of transactions they are sending right now. So Ethereum has to be like 100% backwards compatible. So they when they introduced new fees scheme, they just couldn't drop the support of the previous fee scheme. So instead, they just made an Ethereum improvement proposal that abstracted the transaction and included a special prefix that said that if this prefix is 1, then it is the type 1, which is the legacy transaction. If it is the 2, then it's a new one. If it is 3, then it's something else. And this is how like Ethereum works right now. Maybe in the future there will be new transaction types, and all of them are going like all of them will follow the specification. The chain ID is included in the European coding to mitigate transaction replace on the other EVM chains. Yeah, so in the transaction structure, there is no chain ID, but the chain ID is included in the encoding itself, which mitigates the replace. And this like inclusion of chain ID was introduced in a separate EAP and wasn't a part of the original Ethereum, because when the Ethereum launched, it was the only blockchain in existence, like EVM blockchain in existence. And when the new blockchains emerged, like Binance Smart Chain, etc., because all of them use the same Ethereum virtual machine, it is possible to replicate the exact transactions on the other chain. So to mitigate this completely, the chain ID, the unique identifier of the blockchain, is included in the European coding before the signature. And Ethereum mainnet is 1. So chain ID for Ethereum mainnet is 1. And for every other EVM blockchain, it is unique. So when you are sending transactions, you can be sure that it won't be replicated somewhere else. And the transaction hash is a cache of 256 hash of its signed European coded counterpart. Yes. So when you construct a transaction, then you encode it with a special recursive length prefix encoding. You get like a raw bytes of the transaction. Then you sign it with the ECDSA, get the signed transaction and the signature. Then you get this signed transaction and the signature encoded once again via the RLP encoding, get another bytes. You hash it with cache 256, and the output is the transaction hash. So basically, every major field together with the unique nonce and the signature gets you unique transaction hash. And if you were attentive enough, the from field is actually absent in the transaction. And block explorers are smart enough to deduct this field from the signature and the transaction. So basically they recover the address from the signature and put it in the from field. But the transaction itself comes without the from field. Yeah, okay. So the transaction lifecycle. First of all, the transaction is constructed, then encoded, signed, then again encoded. And this encoding then hashed to calculate the transaction hash. Then transaction is broadcast to the network and added to the mempool. Between those two actions, a lot of validation takes place, and a lot of DDoS protection takes place. So if everything is fine here, then the transaction is added to the mempool. Mempool is a special place of nodes, all the Ethereum nodes, where transactions live and are publicly available, so anyone can just inspect what happens there. After the transaction is added to the mempool, a validator picks a transaction from it and includes it into the block. So Ethereum allows any order of transactions to be included into the block. It is absolutely the validator's choice, but usually they pick the most expensive ones to maximize the profit. But it is up to validator what to include and what to not include. And once the transaction is included into the block, the validator executes the block strictly in the order of transactions, so one by one. And when it is executed, it is added to the chain and further broadcast to the peers of this node. Okay, so enough with transactions. Let's take a look at the blocks. So actually, blocks are just batches of transactions that are mainly needed for the optimization purposes. So it is actually possible to construct a blockchain that will consist of transactions, but only of transactions. But this is wasteful. A lot of resources are needed to maintain such a blockchain. So for the optimization, these transactions are actually packed into the blocks. And usually, if you are writing smart contracts, you will be using some kind of local blockchain, and those local blockchains usually have blocks that are only with a single transaction. So once the transaction is included, the block gets validated. But in the real world, blocks have a lot of transactions because like the decentralized network can't keep up. Yeah, and here we have the state of Ethereum. Once the block is added and executed, the state changes to T+1. And the transactions are executed in order, like T1 will be the first, T2 will be the second, and etc., etc. Yeah, so what is inside a block? Right now, the Ethereum block is a complex structure that contains both the intricate proof-of-stake consensus information and the transaction execution payload. Before Ethereum switched to proof-of-stake, blocks only contained the execution payload. So basically, this was the header of the block and the list of transactions that this block had. But after the merge in the block, the whole proof-of-stake consensus information was added on top of the previous execution payload. So execution payload is contained within the new proof-of-stake consensus, and it contains the list of transactions. So here is the a diagram that is quite complex, but I'll take a look only at the execution layer of the Ethereum on this lecture, because the consensus layer is actually out of scope of this course. It is a super advanced topic, and yeah, we won't cover it. But still, we have a proof-of-stake consensus block, which consists of three main tables. The first one is the administration table, which contains the proof-of-stake beacon state information. That's the slot that beacon chain right now has. It is basically the block number, the proposer index. It is the unique index of the validator that proposes this block, a parent root, a hash of the previous block in the this huge block. And this parent root is actually the same hash as the hash used in the execution layer. So they're just duplicated. The state root, it is the state of the beacon chain, the roots of the Merkle tree that holds this whole state. The random reveal, it is the random data that the validator provides when the new block is added. The graffiti is just an arbitrary data that validator may provide for, some advertisement or whatever. So usually the mining pool is set there. And the signature, it is not the ECDSA signature, it is the BLS signature here. Yeah, and that is it for the administration. Then the consensus, the deposit root, it is the roots of the Merkle tree that holds the validator deposits up to this block. The deposits count, the attestations. These are the unique attestations of aggregated attestations of every single validator that's voted for this block. They are also account with BLS signatures. Then deposits. The deposit root is the topmost state, but deposits are the actual list of deposits in this block. The proposer slashings, it is also connected with the consensus. The voluntary exits, it is something that will be added in the Shanghai hard fork, probably in a couple of months. And slashings, like another type of slashings. Yeah, and also some information about committees, which are how the validators are aggregated to attest for each block. And beneath this comes the regular execution layer, which is the one on the right, which has the header and the transactions. So let's again have some questions. Exactly blocks store. Yeah, let me just go here. Where exactly block stores in blockchain? Is there any size limit each of them? Yes. So if you are talking about transactions, there is a special limit that I will talk about in the next slide. So it is the limit that limits the execution amount of every transaction that is included in this block. Right now it is 30 million, and you just can't send a transaction that will consume more than 30 million gas. If it does, it just won't be included to the block at the stage of validation. So if you wanted to, if you are broadcasting this transaction, the node will check how much gas this transaction consumes, and if it consumes more than block allows, the node won't just accept this transaction. And where do those blocks exactly? So if we are going really deep into how node works, it is just a regular database, and the whole blockchain is here. So every block has the hash of the previous block, and those blocks just get stored into a regular database, and that's it. And age, yeah, so every block has a timestamp. I will talk about this in the next slide. So proof of stake has only one validator, and what happens if it does not have time to validate a new block in 12 seconds? Yes. Proof of stake consensus decides who will be the next block proposer, who will be the next validator to construct the block. And if this validator fails to construct the block, there are actually several outcomes. The first one is nothing happens. The second one, the validator gets slashed. So in the proof of stake consensus, in order to become a validator, you have to stake 32 Ethereum right now. And this Ethereum is like a collateral that is used to reward and to slash the validators. So nobody wants to lose Ethereum, lose Ether, so they behave correctly. But if validators do something bad or behave somewhat like Ethereum doesn't like, they get slashed. And yeah, so actually this like there are a lot of cases, like really a lot of cases when validator can become slashed, and it actually depends on the validator itself. So sometimes he may just be skipped and the empty block is included and everyone is fine. But sometimes, for example, when this validator purposely like misses the blocks, Ethereum can identify that and slash him. So we can access whole blockchain database from our local, do not consume our local storage completely. Yes, so of course you can access the blockchain database from your local. So draw a lot of types of nodes that Ethereum has to maintain: the archive node, the full node, and the light node. Maybe there are more. The archive node, it is the node that contains everything, every single transaction, every single bit of information that has ever happened to Ethereum. The full node doesn't have the information about the whole Ethereum, but it contains the roots of every like major data structure up to a certain point. So full node has access to at least 256 blocks deep. That is why when you are, for example, forking the blockchain, you have to actually specify the archive node, otherwise it won't work. And the light node, which fully relies on the full node, yeah, and it just works like in pair with the full node. For example, when you are sending a transaction, you need to estimate the cost. Light node can't do that, so it delegates the estimate to the full node and receives the correct estimate. But yeah, it is something that can be like run on the cell phone, if you will. Yeah, and it may consume the full storage completely. That is why you need like high capacity servers to run Ethereum nodes. Okay, so what is inside the execution layer of the Ethereum block? So first of all, the parent hash. It is the field that makes like the linking of the blocks with each other. So it is the field that makes Ethereum a blockchain. So every current block contains the hash of the previous block, which is really important. Then there is the block hash like of the current block, which is the hash of the contents that current block has, which includes the hash of the previous block. And actually this hash, the block hash, it is the state of Ethereum like right now. So this block contains pretty much everything that Ethereum has right now. You can, for example, validate that that the account had X Ether on its like balance, and with some like manipulation with some data structures, if your block hash is the same with this block hash, this means that you are correct. So having this hash pretty much makes you validate anything that has happened on Ethereum. The block has the fee recipient field. It is the Ethereum address that will receive the reward. Actually, the tip of every transaction that is included in this block will be sent to the fee recipient, and the base fee of the block that each transaction specifies will be burned. Then there are 4 fields that stand for the state of the Ethereum, the actual state, the transaction receipts. So these are 3, sorry. So the state, it is the smart contract state, the receipts, the transaction receipts, and the transaction routes. So what it means is that there are special data structures, the Merkle-Patricia trees, that Ethereum maintains in its database, and those special data structures maintain the state of Ethereum. The first one, it is the tree that in every leaf of this tree has another tree, which in turn stands for the state of smart contract. So we have the smart contract. It has a special state, and this state is encoded in the Merkle-Patricia tree, and then placed into the leaf of the bigger Merkle-Patricia tree, which is then calculated via its algorithm, and the root of this big tree is obtained. And this root stands for every single state of every single smart contract present in Ethereum. Then there is this Merkle-Patricia tree for the transaction receipts. It is the metadata of the transactions, like how much gas it consumed, its hash, and etc. etc. And also the root hash of the transactions that are right now in this block. So every block has a list of transactions that are included in it, and they're also placed in the Merkle-Patricia tree. And with the same algorithm, the root of this tree is computed and included into the block. Then there is a logs bloom, which is basically a special data structure that contains event logs for its quick access. The preference field, which is after the proof of stake, which was introduced after the proof of stake switch, and it is used instead of the mix hash field. The mix hash field is deprecated and substituted right now, and the mix hash field was used in the proof of work consensus. And right now, because Ethereum is a proof of stake, they decided to not introduce the another field and to reuse the obsolete one. And this preference DAO is just a special proof of stake consensus field that is pseudo-random and can be accessed via the EVM. So Solidity has an access to this field, which might be used in pseudo-random stuff. And then there is difficulty field. It is also the legacy one from proof of work consensus, but right now this field always equals to 0, and it is just there, like wasting space. Gas limits and gas used fields. First one is the maximum gas allowed for transactions to use, which I have mentioned right now equals 30 million gas. But yeah, for example, Binance Smart Chain has this gas limit of 100 million, so 3 times more than in Ethereum. And the gas used, it is the actual amount of gas that the transactions that are included in this block used. This number can't be more than 30 million, but it can be 0. So blocks can be empty, and it is fine. So what is cool about this gas limit is that it is adjustable after the London hard fork. So Ethereum tries to maintain the amount of gas that transaction consumed to be 15 million, which is 50% of the gas limit. And if this consumed amount increases, then Ethereum tries to increase the base fee, so to lower this used gas. And if this used gas is lower than 15 million, then the base fee will decrease, so to offset. Then there is the base fee per gas field, which was introduced after the London hard fork, and the transactions that set their gas lower than this base fee won't be accepted by the node. So every transaction has to specify at least this amount of gas, and this gas will just get burned. Yeah, which makes Ethereum deflationary. And the block timestamp, the Unix timestamp of the block, which is right now fully predictable and comes every 12 seconds. Okay. Does something get executed on execution layer right now? Didn't the merge move all the blocks to the consensus layer? So, like, there is software that is right now responsible for the execution of the blocks, and there is software that is responsible for the consensus. And these are like 2 different types of software that communicate with each other through the like local RPC, which is local to the node. So it actually depends how you interpret the question. So it is the node that executes both, but this is like these are different like softwares that actually executes them. What is execution block? Actually, it is just an abstraction over the legacy block with London modifications. So it is just like part of the block the Ethereum right now has. How transaction hash, block hash calculated? Yeah, so transaction hash is the hash over the signed RLP encoding, and block hash, it is just the Keccak 256 hash of its contents. Okay, the block life cycle. Number 1, the block validator is pseudo-randomly but deterministically chosen via proof-of-stake consensus algorithm. Yeah. So every validator every next validator is deterministically known. So you can be 100% sure that the next block proposer will be this validator, but you can't be like 100% sure that the next validator will be like this one, because every block and the validator provides a special random which changes the outcome, which changes who will be the next validator, but it is fully pseudo-random and also like deterministic to a certain point, because like it is actually impossible to be 100% random in the decentralized world. Second, validator assembles the block as he wishes to maximize profit. Yeah, once the validator is chosen, he assembles the block with the transactions as he wishes to maximize profit. And here is the miner extractable value in braces, which is also an add-on to a node. Every node provider or like node holder can install the special software, like Flashbots software, which will provide an additional mempool of transactions with like certain profit to extract from those transactions. So miner extractable value is like a whole huge concept that might cover like a separate lecture, but yeah, this software usually sets how the blocks are like assembled, and right now I believe like 70 or 80% of validators in Ethereum use this software. Point number 3, validator executes block transactions one by one and sends the block to peers. Yeah. And point number 4, at the end of the epoch, attestation of block validity begins. So every 32 blocks, new epoch starts, and those like 32 blocks are assembled into the like epochs. And once the epoch is finished, the attestation on the validity of this epoch and the validity of every single block begins. So every 500,000 validators start voting whether they think the block is valid or not. Then those votes are assembled by special committee leaders. Then they're further assembled, and the block proposer then takes those assembled attestations and includes into the block itself. So this process is called attestations, and it happens every 32 blocks once the epoch finishes. Point number 5, block gets marked as safe. Yeah, this is when the attestation period finishes. The epoch gets marked as safe, which means that it is unlikely for it to change, but still there is a chance. And point number 6, after another epoch gets marked as safe, so when another epoch is placed on top, our like observed epoch gets marked as finalized. At this stage, pretty much no one and never can change the history of Ethereum. Why? Because the block gets marked as safe when it receives 2/3 of the, like, if the 2/3 of attestations are in favor. So every validator has to attest, and if they doesn't, then they get slashed. But if 2/3 of the whole, like, 500,000 attestations are in favor of the block, it gets marked as safe. And if there is another epoch that is marked as safe, that means that another 2/3 of validators have voted in favor. So 2/3 like intersects with another 2/3, which means that in order for somehow manipulate the state, the attacker has to be in control of 1/3 of validators, which is like billions and billions of dollars. And nobody has this power. Does validator verify each transaction manually, or it happens automatically via software? So of course it happens automatically via software, but it is really complex software. Yeah, and this software is called proof of stake consensus. Epoch is just like an abstraction over the set of blocks, which contains 32 blocks. So it is also another kind of optimization that Ethereum like has, because it is a highly decentralized blockchain, and receiving attestations for every block is like impossible. So instead, it receives attestations for each epoch, which is 32 blocks. It's like 6 something minutes. Okay. So actually, this is it for the lecture. And if you have any questions, please go ahead.
Yes, it is time for additional questions. And if there are questions in the chat that you did not answer, please take a look.
It is in QA?
No, it's ordinary chat. Some of this, but maybe it's okay.
Yeah, so if I haven't answered something, please ask again.
Okay. Expect a presentation and quiz in the classroom from us, and see you soon. And we will talk about smart contract.
Actually, not. The next lecture will be about cryptography in Ethereum.
Okay. Okay.
Yeah.
Thank you. Okay. See you soon and goodbye.
Yeah, goodbye. Thank you.